So on continuing with the dynamic force analysis, we will discuss a very important topic called the dynamically equivalent system. So why should we go for a dynamic equivalent system is what we are going to briefly discuss in the short video, and followed by the turning moment and the flywheel, that is turning moment diagram and flywheel, a brief explanation. In the other video I will be showing you some examples on the turning moment diagram and the flywheel based problems. Okay, now we'll start with a dynamically equivalent system. You can see the shape represents almost the shape of a connecting rod. So why should we go for a dynamically equivalent system? In the previous section, the expression for the turning moment of the crankshaft has been obtained for the net force F on the piston. This force F may be the gas force with or without the consideration of inertia force acting on the piston. So if you go back to the previous slides which I gave you during the class hours, a number of formulas were given which was talking about the crank effort, the piston effort, for the vertical engine, for a horizontal engine. So this is a slight extension to those topics. As the mass of the connecting rod is also significant, the inertia due to the same should also be taken into account, because the force F may be the gas force with or without consideration of inertia force acting on the piston. So in this case, previously we are not considering the mass of the connecting rod. So in this case we have to consider the mass of the connecting rod, because the inertia effect produced due to the mass of the connecting rod is also significant. So as neither the mass of the connecting rod is uniformly distributed nor the motion is linear, its inertia cannot be found as such. Why? Because if you see the shape of the connecting rod, the mass will be concentrated more on the right side of the connecting rod than here on the left side, because of its typical shape. See, it is not a cube, it is neither a rectangular shape. The connecting rod, see, in this area the mass is very less. In this case the mass is very large. So if you consider the inertia force, see, what are inertia forces? Inertia forces are due to the mass of the components as well as due to its acceleration. So that is these two factors contribute to the formation of inertia forces, or what you call as disturbing or the resistance forces. So since the connecting rod shape is quite typical, I repeat, this area has a lesser mass compared to this area. That is what being said here. See, its inertia cannot be found because the mass of the connecting rod is not uniformly distributed. It's not uniformly distributed because of the shape, or the motion is linear. So the motion of the connecting rod is neither linear nor the mass is uniformly distributed throughout its length. So that's the reason we go for a dynamically equivalent system. So dynamic equivalent system means the rigid link is replaced by a link with 2 point masses. So we assume a rigid link, and this rigid link is replaced by 2 point masses, and mind you that this link is a massless link. So dynamic equivalent system means that the rigid link is replaced by a link with 2 point masses in such a way that it has the same motion as the rigid link when subjected to the same force. That is, the center of mass of the equivalent link has the same linear acceleration and the link has the same angular acceleration. So if this is the center of mass G, so this link is assumed to be having the same linear and as well as the linear acceleration as well as the angular acceleration. And there is figure 13.6b shows a rigid body of mass m with center of mass at G. Let it be acted upon by a force F. So we imagine that this connecting rod is replaced by a rigid link and a force F is acting, which produces linear acceleration as well as angular acceleration similar to that of the connecting rod we are considering. So we know the expression force is equal to m into F, and F dot E is equal to I into alpha. So the acceleration of G is F is equal to capital F by m and angular acceleration of the body alpha is equal to capital F into small e divided by I, where E is a perpendicular distance of F from G. So this E is the perpendicular distance of F from the center of mass at G, and I is the moment of inertia of the body about perpendicular axis through G. So now, to have the dynamically equivalent system, let the replaced massless link, which I told you, this link is assumed to be a massless link, so which represents this connecting rod, and it has 2 point masses, such that for dynamically equivalent system you have 3 conditions which we will be seeing now. So for dynamic equivalent system, let the replaced massless link has 2 point masses m1 at B and m2 at D. m1 at B and m2 at D at distances of B and D respectively from the center of mass G. So there are 3 conditions which I told you about. The first condition is this: the force F is to be the same. As the force F is to be the same, the sum of the equivalent masses m1 and m2 has to be equal to m to have the same acceleration. So in order to have the same angular acceleration, this summation of the sum of m1 and m2, that is the point masses at B and D, must be equal to the mass m. So this is the first condition. And the second condition will be that the numerator F dot E and the denominator I must remain the same. That is, numerator F dot E, in the angular acceleration of the body, this F dot E and I must be the same, must remain the same. So F is already taken same, thus E has to be same, which means that the perpendicular distance of F from G should remain the same, or the combined center of mass of equivalent system remains at G. So this is possible if the product of m1 into B must be equal to m2 into D. This is the second condition. Second condition for dynamically equivalent system. The first, in second condition, the numerator F dot E and the denominator I must remain the same, and it should be that is, it shouldn't vary. This ratio should not vary, and F is already taken the same. Thus, E has to be same. So this E is the perpendicular distance of the force F, this line of action of force F from the center of mass at G. So this should also, not only the product of F dot E must be the same, and even the moment of inertia I should be the same. That is, the ratio of F dot E divided by I should be the same. Even the perpendicular distance E, this is what is being said, this particular distance E must also remain the same in order to have a common angular acceleration. So this is possible only if m1b is equal to m2d. So this is B from the center of mass G, and this is D from the center of mass G of m2 and m1. So both this product must be, product of m1 into B must be equal to the product of m2 into D. So this is one more condition. The third one would be to have the same moment of inertia of the equivalent system about perpendicular axis through their center, combined center of mass G. We must have the summation of m1b plus m2d must be equal to I. That is the moment of inertia. So to have the same moment of inertia, the summation of the product of m1b plus this the product of m2 into d must be equal to the total moment of inertia of the equivalent system. So these are the 3 conditions, and I think the same thing is again repeated. Thus, any distributed mass can be replaced by 2 point masses to have the same dynamical properties if the following conditions are fulfilled. The first one is the sum of the 2 masses equal to the total mass, which we saw here. Second one would be the combined center of mass G coincides with that of the rod. So this happens if this condition is satisfied. Third one would be the moment of inertia of 2 point masses about perpendicular axis through their combined center of mass is equal to that of the rod. So if these 3 conditions are satisfied, then the system will be a dynamically equivalent system. So now we come to another important topic, that is turning moment diagram and flywheel. This forms as module 2, part 3 of machine dynamics, B.S. Abdurrahman University syllabus. I think you are aware of this 4-cylinder engine setup. So this is the connecting rod, this is the crankshaft, and this is the flywheel. Flywheel is attached to the crankshaft. This represents the piston, So this is the crankshaft, and this is the main bearing journal, and this is the oil passages which lubricates, and crankshaft balance masses. So these are the balance masses for the crankshaft. So this balancing of reciprocating masses or the rotating masses, we'll be seeing it in module 3. That is another a very important and vast topic. Anyway, right now we'll concentrate on the topic of turning moment and the flywheel. So this is how it looks like. This is the cylinder, this is the piston rod, this is the crankshaft which we saw here. Crankshaft nose, this is the crankshaft nose, and this is the piston, this is the piston rings, this is the intake valve, spark plug, exhaust valve. This is a basic setup, and we'll go for a 4-stroke engine cycle. This is a suction stroke, you call this a compression stroke. So this is the power stroke where enormous energy is generated, and this is the exhaust stroke which removes the exhaust gases which are to be removed or exhausted or removed from the cylinder during the exhaust stroke. This is the 4-stroke engine, and these are the basics of automobile engineering, and these are some of the explanations. So what do you mean by intake? There is intake, or the 4-stroke cycle starts with intake stroke, with the piston is at the top of its travel, and the inlet valve opens. As the piston moves downwards, it sucks the working fluid. And into the cylinder under the atmospheric pressure, and the exhaust valve remains closed. This is the compression stroke. When the piston reaches the bottom of its travel, the inlet valve is closed and the working fluid is compressed as the piston moves upwards. So this is the compression stroke. So this is the power stroke after the ignition. So the piston reaches the top of its travel. In the case of an Otto cycle engine, a spark ignites the air-fuel mixture, initiating the power stroke, in which the burning gas expands and forces the piston downwards. In the case of diesel engines, the fuel is injected into the compressed air, which spontaneously ignites, initiating power stroke. As in the Otto engine, both inlet and exhaust valves remain closed. So both the valves, they remain closed, inlet and the exhaust valves. And this is the exhaust stroke after the power generation. As the piston moves through the end of its downwards travel, the exhaust valve is opened, and the upward movement of the piston expels the exhaust gases. After the exhaust stroke, the cycle starts again. These are some of the basics of automobile engineering. Now this is a gudgeon pin. So this gudgeon pin is the one which connects the connecting rod with the piston. So this is the gudgeon pin. This is how it looks like. So another portrayal. This is the gudgeon pin. This is the piston. This is the piston ring. This is the connecting rod, and this is the crank pin. This is the crankshaft which is attached to the flywheel. And there is another photograph. So flywheel which is depicting the different areas. This is the crankshaft nose. This is how it looks like. Flywheel, a crankshaft mechanism. And this is another flywheel crankshaft setup. A very basic setup. There's a flywheel, as you can see. Okay, before we get into the problems on turning moment diagrams, we will talk about what do you mean by a turning moment diagram, what do you mean by flywheel, its functions, etc. Okay, now turning moment and the flywheel. The turning moment diagram is a graphical representation of the turning moment or the crank effect. The turning moment is also called as the crank effort for various positions of the crank. So this graph between the turning moment is the turning moment, and theta is the crank angle, the angle through which the crank rotates. So the graphical representation, the turning moment diagram is a graphical representation of the turning moment or the crank effect for various positions of the crank. That is theta. This is Tm or T. So it is plotted on Cartesian coordinates. So on the y-axis you have the turning moment data, and the x-axis you have the theta angles. So for example, this is 0, this is pi by 2, this is pi, and so on. So I will give a brief explanation about this graph. It's a very important graph which explains to you about how the flywheel stores energy. So where the actual addition and subtraction of energy takes place. So this turning moment versus crank angle is a very important graph for an automobile engineering setup. So we know what is the turning moment on the crankshaft in the previous slides which I distributed during the class hours. The turning moment or the torque T is given by Fp into R sin theta plus sin 2 theta divided by 2 into square root of n square minus sin square theta. You know, theta is the crank angle, and you know what is Fp. Fp is the piston effort, R is the radius of the crank, and n is given by L by R. That is ratio of the connecting rod L divided by the radius of the crank, and theta, as I told you, the angle turned by the crank from the inner dead center. So these are the values of theta. Okay. Now I will give you a brief commentary on this turning moment versus crank angle graph. Very important. It forms an indispensable part of automobile engineering. Okay, see, from the above expression we see that the turning moment is 0 when the crank angle is 0. So when at this position the turning moment is 0 when the crank angle is 0. It's quite understandable. It's very easy. So it is maximum when the crank angle is at 90 degree and is again 0 when the crank angle is 180 degree. This is shown by the curve ABC in figure 16.1. So in this area, if you see, so the turning moment has its maximum value, that is T max is at point B when the crank has turned through an angle of 90 degree. Again it drops to 0 during that is 0 to pi when the crank angle moves from 0 to pi. At 0 it is again the value is 0, turning moment is 0. Again when the theta value is 180 degree, again the turning moment value comes to 0, whereas this is the maximum value. As you can see, as the crank rotates, the turning moment value also increases. It reaches the maximum level, again the value drops. So that is what is said here. This is shown by the curve ABC, and it represents the turning moment diagram for the outstroke. So this ABC represents the small a, small b, and small c represents the outstroke, turning moment diagram of the outstroke. Now what about the next one? See this area, that is C, D and C, and then as you can see here also small c, small d and small e. Again the cycle repeats, and this line is called the mean torque line. You will be seeing it now. See here, the curve CDE is a turning moment diagram for in stroke and is somewhat similar to the curve ABC. So this is the outstroke and this is the in stroke. So when the crank moves from 0 to pi, again from pi to, again it makes a revolution 360 degrees. So this forms work done per revolution. So it starts from 0, again it moves 180 degree, and from 180 degree it further moves down to 360 degree. So this forms the work, this represents the work done per revolution of the crank. So since the work done is a product of the turning moment and the angle turned, there is a work done is always given by the product of the formula is given here. Once again, we will be going through these formulas where it talks about the coefficient of fluctuation of energy. So this is the work done per cycle is given by the T mean into theta. So this theta is the angle turn, this is T mean is the mean torque or generally product of torque into crank angle gives the work done per cycle. We'll be coming to these formulas in a moment. Let me just give a commentary on the graph. Yeah. So therefore the area of the turning movement diagram represents the work done per revolution, which I told you. In actual practice, the engine is assumed to work against the mean resisting torque as shown by a horizontal line AF. So this AF is the mean torque. So this represents the mean torque value. So this represents the mean torque or the mean torque line. So this AF, it is assumed that the work against the mean resisting torque is shown by the horizontal line AF, and the height of the ordinate small a represents the mean height of the turning moment diagram. So this small a represents the mean height of the turning moment diagram. Since it is assumed that the work done by the turning moment per revolution is equal to the work done against the mean resisting torque, therefore the area of the rectangle small a, capital F, small e is proportional to the work done against the mean resisting torque. So this portion, work done against the mean resisting torque. Whereas the values above the mean resisting torque, these are addition of energy. So this is the excess energy. We'll be seeing these explanation in a moment. And that is what is being given here. When the turning moment is positive, that is when the engine torque is more than the mean resisting torque, the crankshaft accelerates and the work is done by the steam. So this represents addition of energy. This represents the addition of energy. This represents the subtraction of energy. This is a negative loop that is below the mean torque line. That's what is being said here. When the turning moment is negative, that is when the engine torque is less than the mean resisting torque, as shown between the point C and D. Shown between the point C and D, this area negative, that is subtraction of energy. So the crankshaft retards. So in this case it accelerates during the positive loop. The negative loop, the crankshaft retards and the work is done on the steam. Here the work is done by the steam. Here the work is done on the steam. So this shows that there is subtraction of energy. That's all. And if T is equal to the torque, which already we spoke about, if the T is the torque on the crankshaft at any instant, there is instant instant torque value. If T represents, and T mean is the mean resisting torque, and then the accelerating torque on the rotating parts of the engine, capital T is minus T mean. So the accelerating torque is given by by subtracting the mean torque value from the actual torque. So if capital T minus T mean is positive, the flywheel accelerates, and if T minus T mean is negative, then the flywheel retards. So this is what we said earlier. There is a crankshaft accelerates and the crankshaft retards. There is work is done by the steam and work is done on the steam. So the T minus T mean is positive, the flywheel accelerates, and T minus T mean is negative, the flywheel retards. Now this represents the turning moment diagram for a 4-stroke cycle IC engine. As you can see, this is the positive loop, these are all the negative loops, and the positive loop happens usually during the working stroke. We saw in the previous diagram about the suction, compression and the working stroke. Now during the working stroke there is a positive loop occurs in this area, and this is the exhaust. That is during the exhaust stroke. So a small explanation, the pressure inside the engine cylinder is less than the atmosphere pressure during the suction stroke. Therefore negative loop is formed. During the compression stroke the work is done on the gases, therefore a higher negative loop is obtained. Whereas during the working stroke the fuel burns and the gases expand, therefore a large positive loop is obtained. So here this is the large positive, that is excess energy is produced above the mean torque line. And during the exhaust stroke the work is done on the gases, therefore negative loop is formed. So it may be noted that the effect of inertia forces on the piston is taken into account. So this is what is representing here. This is the resultant turning moment, this line, and this is the mean torque line. So this is addition of energy, this is subtraction of energy. So this is the mean torque line. A1, A3, A5 represents addition of energy, whereas A2, A4, A6 represents subtraction of energy. In the next video, we'll be seeing about the determination of maximum fluctuation of energy and other explanations. Thank you for watching.